Hey everyone. So this new unit here is all about two-dimensional motion and trajectories. And really what we're going to be looking at are two different types of projectile motion. And we're going to start today with horizontal projectile motion. And this is going to kind of tie in your knowledge of vectors and motion of objects and kinematics kind of into one topic. And we're going to treat, if you think about a projectile or something in motion, something that's maybe thrown horizontally. It could be throwing a baseball that is thrown is going to kind of have a motion parabolically as it falls towards the ground. And we're going to treat any type of projectile motion as if it's two-dimensional motion. We're not worried about a third axis, and we are actually going to treat the motion of the object in two dimensions separately. So we're going to look at motion of objects in the y direction and in the x direction, and we're going to treat those paths that the object's traveling, both in both of those directions, individually. So the motion of an object traveling in a two-dimensional plane can be described, if we look at this a certain way, by separating its motion into two components. The horizontal component, which would be our x-axis, and the vertical component, which is going to fall on our y-axis. And we can look at this as far as splitting a vector of displacement, of velocity, of acceleration into its horizontal and vertical components. And the component that's parallel to the horizon is known as the horizontal component. Horizontal. Who would have thought it? Horizontal component. And a component at a right angle or perpendicular to that horizon, which is going to be our vertical component. And we're going to look at this through this type of motion in 2D as a projectile that's fired horizontally. So we're going to look at motion that's kind of half of a parabola, as if an object falls towards the ground, as opposed to an object, and we'll do this later, that's fired from the ground and falls back towards the ground. So those are the two that we'll kind of look at over the next couple days here. So an object that's projected horizontally from some height, let's say this was a cliff here. So if an object is fired horizontally from a cliff or some height above Earth's surface, it's going to obey Newton's laws of motion, which we'll get into specifically in our next unit. But if we neglect air resistance, which we like to do in this course, the horizontal component of the velocity, so if we think about that motion in the x direction, it's going to remain constant. In reality, if an object's moving left to right, moving through air, it is going to slow down, lose speed, and not travel as if it were not exposed to any type of air resistance. But we kind of think of all this motion in a perfect world, and we'll see that as we get into friction later. There's a lot of things that we ignore within the realm of Regents chemistry, and this is going to be one of them. So we'll neglect air resistance and assume that the velocity of an object in that x direction or along the horizon is going to remain constant. Before the object falls, the initial velocity in the y direction, or the vertical velocity, it's going to be 0. It's not moving, hasn't been projected, hasn't been launched yet. But as it does fall, the velocity is going to increase. It's kind of a rough increase there. Increases. And that's due to the object accelerating downwards due to gravity. So we have gravity that is a force pulling the object that's falling towards the surface of the Earth. So that's going to cause the initial velocity in the y direction to be less than the final velocity in the y direction. And we'll pretty much look at this as the final velocity not being 0 when the object hits the ground, but the moment right before it does hit the ground, what would its speed be? Now we're going to take a look at this through an example here and see what this might look like. So we have a plane flying horizontally at an altitude of 520 meters and has a velocity of 280 meters per second heading east. The plane drops the supply packet to a work crew on the ground. The supply packet falls freely without a parachute, assume no wind, and negligible air resistance. So we're going to have no other forces opposing the motion of that packet, and it's going to fall with no other forces other than gravity acting on it. So we'll try and determine two things here. The time required for the packet to hit the ground, and the horizontal distance from the target area that the plane must drop the packet. Now, with these types of problems, or really with any type of motion, kinematic type problem, projectile motion, you should be drawing some type of simple sketch. It doesn't have to be to scale, but it should kind of show what's happening here. I'm going to do my super nice, awesome plane here. So we have a plane. Got to have the back tail on it here. That's carrying a supply packet. I tend to use them as crates, but supply packet, mine are always boxes with X's in them that make them look like crates. So we have a plane flying horizontally. We have motion here in 2 dimensions. We have the plane traveling left to right along the horizon, and it has some velocity, and that's going to be, let me get that a little bit more clear. This velocity is going to be in the X direction. There's also some type of initial velocity. We'll call that initial velocity in the Y direction. It's pointed downwards. And since this crate is attached to the plane, they're considered as one piece. So however fast the plane is moving is how fast the crate is moving. And that'll remain the same until that plane actually drops the crate off. Now we have, with this plane, the distance that the plane is off of the ground, which is the distance in the Y direction. And this plane is going to have to drop this packet to a target. Do a little bullseye there. And this is our target. The plane's going to have to drop this crate some distance in the X direction before it gets to the target. Because that crate's going to be moving forward with the same velocity that the plane has. It's going to follow a parabolic trajectory towards the ground. So we're going to have to release it. We can't release it right before, right above the target unless we weren't moving. So we're going to have to drop it some distance before the target so it can hit the crew on the ground. So the first thing that we'll try for here, well, let's identify some things and see what we know. Let's try and label this diagram here. What do we have? Well, we know that this distance in the Y direction, we know what that is. That's 520 meters. It's flying at an altitude of 520 meters. So as we define the motion of this crate in this plane, we're going to try and look at it in 2 dimensions, in the Y direction and in the X direction. Our initial velocity in the Y direction of that crate, because that's what we're going to be dropping here, is 0 meters per second. We know the velocity of the plane in the X direction, which is 280 meters per second. We don't know this X distance. That's going to be our B. That's the distance, the horizontal distance from the target area that we must drop the packet. We're going to have to solve for that. The distance in the X direction that we have to drop. We don't know that yet. We also don't know time. how long is it going to take for this to happen? That's going to be our A. So this is A, and this is B. The other thing that we do know is the acceleration due to gravity, which is 9.81 meters per second squared. And for now, since our crate's going to be traveling downwards with the force of gravity, we'll consider that a positive direction. We'll keep our acceleration due to gravity positive for now. So this crate is going to be subjected to basically free fall. It'll fall freely with the only force acting on it is the force due to gravity. And there is a certain equation we can use with that, which is distance traveled under constant acceleration. So we're going to use our equation for distance traveled under constant acceleration. And this is going to be in the vertical direction. The equation that we use for that is d equals VIT plus 1/2 AT squared. We're going to rearrange or adjust this a little bit so that it's only dealing with the y component, the vertical component of our motion of our crate. So we're going to look at the initial velocity in the y direction. Time doesn't matter, so we'll keep that as is, plus 1/2 acceleration in the y times t squared. So we've adjusted what variables that we could so that we're only referring to the motion in the y direction. So that's our distance, our velocity, and our acceleration. Let's see what we have here. We know the distance in the y. The distance in the y is, and I'm going to move this up to here, it's 520 meters. And that's equal to our initial velocity in the y, which is 0 meters per second, times time, which will give us a product of 0, plus 1/2 our acceleration in the y, 1.81 meters per second squared, times time squared. This simplifies to 520 meters equals 0 plus 1/2, 9.81 times time squared. We multiply by our 2 here to cancel this, our fraction of a half. And what we end up with is 9.81 t squared equals 1040. We can divide out our acceleration. T squared equals 106.014. We'll take the square root of that to get rid of our squared. And t comes out to 10 seconds. So the time it's going to take for that packet to hit the ground from that distance while being accelerated at a rate of 9.81 meters per second squared towards the ground, that's going to take 10 seconds. Now this crate, as it moves towards the ground, is going to fall with a parabolic trajectory towards the ground as it's moving forwards with its velocity in the x direction and accelerating towards the ground due to gravity. So we got to figure out what this x distance is. And this is going to be on the second part of our problem here. I'll label that there. This was A. So determine the horizontal distance from the target area that the plane must drop the packet. Well, the acceleration in the x direction is 0. The speed of the plane is the same speed of the packet in the x direction. They're attached, they're connected. So they're traveling in the x direction with the same speed. but not accelerated. There is no acceleration occurring here. We also pretty much never deal with acceleration in the x direction. We only deal with it, at least in the scope of this class, we only deal with acceleration in the vertical direction when dealing with projectile motion. We know that the initial velocity in the x direction, which is the speed that the plane is moving, is 280 meters per second. We know that the time it's going to take for that packet to get to the ground is 10 seconds. And we don't know the distance in the x direction. But since we have constant acceleration, even though it is 0, it is constant, we can use the same equation. But we're going to replace our variables here with only x component variables. So we're going to look at the distance in the x, the initial velocity in the x times the time, plus 1/2 acceleration in the x times time squared. Distance in the x we don't know. The initial velocity in the x is 280 meters per second. Time is 10 seconds. Plus 1/2 acceleration in the x is 0. And that's because we have the same speed as plane, which is not accelerating. Otherwise, we'd be indicated of that. So acceleration in the x is 0 times 10 seconds squared. 1/2 times 0 times 10 squared, well, that gives us 0. And 280 times 10 gets us 2,800 meters. 2,800 plus 0 gets us 2,800 meters. And that distance, that's the point at which we're going to have to drop this packet. That's going to have to happen if we think of a compass here. That's going to have to happen west of the target. That's going to happen 2,800 meters west of target. So there's our answer for B. So that plane is going to drop the packet 2,800 meters west of the target, and it's then going to hit the ground on the target 10 seconds after it was released. These are the types of problems we'll come across when dealing with horizontal projectile motion. We might see things where objects are being projected off of a cliff, but they're going to kind of follow this half parabola trajectory where they're only falling towards the ground. They're not rising off the ground and coming back. So they're only falling towards the ground, and we see kind of that half parabola trajectory of the object as it takes its momentum moving forward, not accelerated moving forward, but accelerated downwards as the object speeds up towards the ground and eventually stops once it hits the ground. So we'll do some practice with this in class. If you have any questions, make sure you bring them up to me when I see you. Have a great day.